All right, hello everyone. Am I audible? I'm audible. Can you put my slides up on the screen? And my slides are up on the screen. Excellent. I'm going to get started right away because I have a lot of content to get through, so people who are late are just going to have to catch up. So my name's Shane Carr. I gave a talk earlier today about ICU4X. Right now I'm going to give a talk that I'm really excited about text segmentation in complex languages. My qualifications here, I'm convener of ECMA TC39. We do a lot of work with JavaScript internationalization. Chair of the ICU4X Technical Committee. I work on internationalization engineering at Google. So what is text segmentation? So there's a lot of different types of text segmentation, but ultimately it's taking a continuous sequence of text, something where it's just a string of text. There's no breakpoints already in the text, and then trying to find what the breakpoints are. So there's 4 types of units of text segmentation that Unicode supports. Grapheme clusters, words, sentences, and lines. I sort of illustrated them over here with this little string of English text. A lot of times breakpoints occur at the same place as previous types of breakpoints. So in this example, every sentence breakpoint is also a line breakpoint, and every line break is also a word break. That's not necessarily the case in every language. It happens to be in this little string of text that I've given you over here. Other types of breakpoints that we could explore in the future, things like hyphenation, phonemes, and syllables. Currently, these top 4 are the ones that we're focused on. Thanks for everyone who's coming in. I got started right on at 2:50 because I have a lot of content to get through. So I'm just explaining what is text segmentation. So why do you need text segmentation? These are 4 examples of major use cases. One is you need to do line wrapping, one of the most important ones. If you have a string of text, how do you display it on a narrow screen like on your mobile device to wrap the text when you're reading a big Wikipedia article, for example? Another one is search indexing. How do you think that search engines and other things can figure out how to query text to obey your search query? Selection of whole words in text. So if you take your cursor and you double click on a word, or if you're in a mobile device and you try to long press on a word, how does it know what amount of words, what amount of characters to select? Another one is spell checking. So if you have a long string of text, you want to do some sort of analysis on that in order to do linguistic spell checking. That's another example of why you need text segmentation. What makes text segmentation tricky across scripts and languages? So a lot of languages don't use spaces between words. That's the title of this talk. The talk is called No Spaces, No Problem. Many languages don't use spaces between words. And another problem is that scripts can be used for many different languages. Many languages can share the same script. The rules that apply to one language might not apply to another language. So these rule-based methods cannot understand a whole language's vocabulary. The vocabulary, I'm going to explain in a few minutes why dictionaries don't work either. So let's talk about what languages we're really talking about here. So languages that require these complex segmentation models. For line and word breaks, we have a lot of languages from Southeast Asia, like Thai, Khmer, and Shan. Even more languages require these models for both for word breaks, not necessarily line breaks, they need for word breaks, things like Chinese, Japanese, and Javanese. So what this means is that about 2 billion people use languages that require these complex segmentation models. You should care about these complex segmentation models. I see there's about 20 people in this room right now, maybe 30. More people are coming in. That's great. Come on in, take a seat. I'm really, really glad that you're here because this is one of the, this is a really high impact problem that not enough people have really invested in and cared about. And I'm really, really excited today to share what I've learned about it and then hopefully see some next steps. So let's talk about the model that we've been using for text segmentation for many years. It's dictionary-based segmentation. So segmentation uses it's based on a predefined set of words. Maybe in a particular language, you have a dictionary, you've got a list of, thousands and thousands of words. And what you do is you take a string of text, you sort of look ahead to be like, okay, what's the longest word in the dictionary that matches where I'm currently looking at the text, right? It's a very simple algorithm. You probably learned how to code it in your algorithms class in computer science class, maybe. And it's always looking for the longest word from a particular point, and then once it finds it, then it goes and looks for the next word and the next word after that. So this has been around for a long time. It's what most phones and devices use to do segmentation. It hasn't evolved for 25 years, 30 years. This is what people are still doing, for the most part, is this dictionary-based segmentation. But Where does dictionary-based segmentation fall short? There's a lot of key points here. One is that dictionaries are very large to ship on device, and it means that a lot of devices only support a very small number of scripts and languages because, for reasons I talked about earlier in my ICU4X talk, like it's not feasible to ship models to ship data for every language. And in CLDR, we're talking maybe like 10 kilobytes to add a new language. When you add a new dictionary, you're talking about like hundreds of kilobytes to add a new dictionary. So that's one problem. A second problem is that dictionaries evolve and you can't recognize new or specialized words in the language. So if you're a speaker of English, you might know that words that have an ing in them might have a certain semantic meaning, certain content. With a dictionary, you have to have every ing word in your dictionary. Something that you can do with an ML model, for example, is learn that if you see ing, it might be the end of a word, right? So ML models can learn about how language is structured much more than just raw dictionaries. A third is that this longest match algorithm that we always use, it can break, and there's lots of examples here where the longest match might not actually be the correct answer. So there's two different broad cases here that I'm going to sort of focus on for this problem. One is the Southeast Asian and East Asian languages. So with Southeast Asian languages, the type of problem we're solving is that you have like 100-ish code points per language, right? You have like some sort of relatively fixed set of code points you can use in your language. And words are like 3 to 7 code points in length. And then a different problem is CJK, where you have tens of thousands of characters, lots and lots and lots of characters, but the words are much shorter, typically. Again, there's exceptions. That's why I sort of like put big fuzziness in the words I used here. But these are sort of two different types and classes of problems. And when we've been looking at solving these problems, we sort of look at these as sort of two different types of problems. I will talk a little bit later about when we took a model from one and tried applying it to another. So let's go ahead and dive in. This is going to be a technical session. It's the Unicode Technology Workshop. I'm allowed to talk about technical things. So let's go ahead and dive in. So first I'm going to talk about CJK. So I'm going to talk about this first model. You may have heard about this one, BudoX, AdaBoost. So what is AdaBoost? BudoX is a little open source library that segments CJK text. It takes each point in the text where there might be a breakpoint, and what it does is it looks backward and forward. It forms n-grams, and it takes basically, it evaluates a whole bunch of different types of n-grams and uses all the different n-grams to form a signal in order to figure out whether or not the breakpoint is good. A very naive model that has been experimented before and doesn't work, so no one uses it, is a bigram model where you just take two characters and you train a model to try to figure out between those two code points, is there a breakpoint? This AdaBoost does this, but it's a little bit more general. It doesn't look at just the bigrams. It looks at trigrams. It looks at individual code points and other things. Approach 2. You're the first people seeing this. It's the first time I'm presenting this in front of anyone. A new model that we're calling RadaBoost. It's a radical-based AdaBoost. So this observes that in a lot of Han script text, you have radicals, and those radicals are core components of the Han characters. And what if we can actually use these to give us some signals about whether or not there should be a breakpoint at a particular point in the text? So there's some examples there about some radicals. One that refer to water, and you see that is used in river and sea. Since certain radicals frequently appear together, we can then use those as hints, as clues. And with AdaBoost, we can throw those in along with the n-grams to see what we can get in terms of new segmentation models. I want to highlight Shenghang, who has been our Google Summer of Code contributor, and he's stayed involved with the project since he did his Google Summer of Code project this last summer. This was his idea. He implemented it from scratch, and it's great, and he's also done the experimental code in ICU4X. So this is a really cool graph, because this sort of illustrates, I'm going to spend a little bit of time on this slide, because this illustrates what's going on between BudoX and RadaBoost, right? So this sort of shows what information feeds into determining whether or not there's a breakpoint. So look at the text on the right. That's the text we're trying to segment. We're looking between characters C and D. So there's 3 characters before and 3 characters after that we consider to see if there's a breakpoint between characters C and D. That's the point where we're looking. The question is there a breakpoint at this point in the text, yes or no? That's the question we're asking. So here's all the different things we can look at. So one is we can look at individual code points. Let's go look at the first row is character A. So that says, look at the character 2 before my breakpoint, or I guess 3 before my breakpoint. And based on just that character, does that give me a signal for whether there is a breakpoint here? BudoX uses that. It also uses the one that's 3 in the future. AdaBoost does not use that. AdaBoost does look at the ones that's 2 before and 1 before, as well as 1 after and 2 after. So those are sort of unigrams, if you will. It also looks at bigrams. The main bigram is CD. Both models look at CD. Those are the 2 characters on either side of the breakpoint. BudoX also considers BC and ED, which are sequences that don't cross over the breakpoint, but are the context immediately before and after. There's also trigrams. AdaBoost doesn't use those. BudoX uses trigrams. And then the radical one, radicals are only found in AdaBoost. They're not found in BudoX. And you can see how those are done. So C prime means the radical of code point C, and D prime is the radical of code point D. So let's go ahead and see a little bit of data here. So there's many variables we're trying to optimize with this. Data size is one of them. Because, again, we can't ship these models if they're too big. No one's going to accept them. So we have to figure out how we can fit these into small binary size. Because otherwise, it's just it's good for writing a research paper, but it's not actually good for deploying to real devices. So let's look at data size. The ICU dictionary for CJK is 2 megabytes. 2 megabytes. Why? Because there's a lot of words and there's a lot of code points. It's a big dictionary, 2 megabytes. The BudoX has different models for different languages. So traditional Chinese is 64K, simplified is 63K. The AdaBoost is 60K. And Shenghong deployed it in a way that it covers all the Chinese variants, which is kind of cool. One model that he trained on all the different variants. We'll see in just in the next slide what that means in terms of accuracy. So here's some numbers. Exciting, okay? Here's some numbers about the accuracy. So the F1 score, all these cells, these numbers are the F1 score. It's sort of like accuracy. It's a thing they use in the machine learning space to sort of take precision and recall and sort of combine them into a single number. So higher is better for these numbers, the F1 score. So, and each column is a different type of text we're looking at. So one thing that Shenhong really looked a lot into is, can we make the model work not just for Mandarin Chinese, but also something like Cantonese, right? Like other languages that use the same script as the biggest language that's in that script, right? So we've got Cantonese, we have traditional Chinese. We have 2 different versions of traditional Chinese because we found that the type of training data that we're training on, whether or not we train with or without punctuation characters, affects the performance of the model. So again, that's something we'll be looking more into, but we'll show both on the slide for now. Same with simplified Chinese, both with punctuation and without punctuation. And we can see what the performance looks like. So first is the ICU dictionary. We can read across there to see what that looks like. ICU dictionary, 79 F1 score on Cantonese. That's not very good. Not very good. We want to be in the 90s. The 80s is okay. 70s is not good. So ICU dictionary, not so good for Cantonese. It does okay for the other cases, traditional and simplified Chinese, because again, it's using a Chinese dictionary. It's not using a Cantonese dictionary. If we run a model that's based on a Cantonese dictionary, and this one is not in ICU. This one is just a Python package that we tested against. It's a Cantonese dictionary. It gets a really, really good F1 score on Cantonese, and okay on traditional. Doesn't support simplified at all. Okay, and then let's look at the 2 ML models, the 2 AdaBoost models. So the AdaBoost models, BudoX for Cantonese, was never trained on Cantonese. So again, terrible. 70s is bad. Not so good for there. It does okay on traditional Chinese and simplified Chinese because that's what the models were trained on, and it does okay on those. But let's go ahead and look at AdaBoost, which is the new model that Shenhong trained this summer. You're the first people seeing a chart with AdaBoost on it. Cantonese, it's in the 90s, a 92.5. That's quite good. In traditional Chinese, it also is near the. It's in the same ballpark as the dictionary models. It exceeds the BudoX model. if we do it with no punctuation, we trained it on a script with punctuation, and that's where the difference occurs a little bit. We can see that if we do the version without punctuation, numbers are a little bit different. AdaBoost and BudoX are more competitive with each other when we do that case. But I just want to remind you all that AdaBoost is one model for all the columns, one model, whereas BudoX is multiple different models for the columns, which means that with AdaBoost you actually have less data overall. So yeah, this is pretty cool data. I decided to show this in numbers instead of graphs. I usually like to make graphs, but it's just easier for this data because the fractions make a difference just to illustrate it in terms of numbers. So again, this is a technology workshop. You all can handle numbers. Numbers are not scary to this audience. Let's look at some more numbers. Performance for the CJK. So this is latency. So latency is inference time. This is the main thing with ML models, one of the things we've been trying to improve. So we can improve model size, and we can improve accuracy, but can we make it as fast as the algorithm that you all learned in your algorithms class that is like designed to be the fastest algorithm for string searching? Like, I don't know if we'll ever get to be on par with that because it's just a different problem, right? However, the AdaBoost models do an okay job. And again, so the latency column here, the dictionary is like 1. So if it's like 6x or 10x or whatever, it means that like it takes that much more time to process the same amount of text. So like it's slower. But remember that also what we're looking at here with the dictionary is the benchmark, like the baseline is also very, very fast because again, it's like an algorithm out of an algorithms book, right? It's very hard for us to actually beat that raw speed. But it's not that so, but again, it's a very, it starts at a very low baseline, which means that if you do increase it by even 6x or 10x, is it actually noticeable when you're doing text layout? We've found that no, it's not actually really that noticeable, especially if you're doing text layout like on a phone. If you're trying to find all the word breaks in like a gigabyte of text from like a Wikipedia article, maybe you'll notice some regression there, but also if you're doing that, you're probably running on a server where you have more resources anyway, and you probably want higher accuracy. So that's my explanation for latency. The F1 scores you saw on the previous page, this slide mainly exists so you can see that like we're acknowledging that like, yeah, the ML models are slower. There's trade-offs. Cool. So let's look at some text samples. This is an internationalization conference. These slides don't have numbers, so people who just like to see text, and these slides might be interesting to you. So this is a string, and we took this string and translated it into Han traditional, Han simplified, as well as Cantonese. So this is my friends and I had dim sum. So dim sum is that in pink is that character over there. It doesn't happen to be in the ICU dictionary. I don't know, is dim sum maybe like a more modern word? Maybe it's like a word that derives from Cantonese or Hong Kong or something like that. The dictionary doesn't know about that word. The radical and the BudoX models, AdaBoost and BudoX, learned that word in their data and are able to recognize that word when you do the segmentation for them. So that's the example here, and this is traditional Chinese. Here is Cantonese. Here's Cantonese written with traditional Han script. Again, the dim sum thing is the same, where like the dictionary doesn't know about that word, but the radical and the BudoX and the two AdaBoost models have learned that word because it's in their training data. We see a couple other interesting things here. I'll point to the word together. The two characters in together. The first character, the line means 1, the number 1, and the AdaBoost models, they're probabilistic, and they're like, well, we think that the number 1 has a much stronger probability of existing. So this is one case where like it thinks that 1 is an individual word, but it actually should be tied to the next word. So the dictionary in this case gets that correct. This is a case where we probably just need to throw more training data in order to like make the model learn that actually 1 is only a word, but it's a word by itself. But if it's followed by that other character, then actually it merges and is not a break. There's no breakpoint there. So that's just an example of ML at work, if you will. One thing interesting here is, well, actually, I'll go to the next slide for this one. This is simplified Chinese of Cantonese variant. I've looked at this slide, and I just, yeah, the T-house is an example here. So this is one where the radical-based model was able to find something that the BudoX wasn't able to find. This word T-house in the middle there. It's in the dictionary, apparently. And the radical model was able to find it, but for some reason, BudoX was not able to find it. So that's an example there. And then, yeah, this, I was, back to this second slide. I have no idea what BudoX is doing in that section of the sentence there, the second block. I've got no idea what BudoX is doing. I still haven't figured that out. But dictionary and radical have gotten that part right. Cool, so these are some text samples. I'm about halfway through my time slot. So now I'm going to talk about Southeast Asia. We're going to do the same exercise. Okay, so I'm going to talk about some models that we use for Southeast Asian. So again, if you remember the slide I gave earlier, CJK, lots and lots of code points, short words. Here we have not as many code points, long words. Okay, cool. So LSTM is one model that we're looking at. So what is an LSTM? It's a machine learning model that uses context from the past and context from the future to try to make a decision about whether to create a breakpoint. The advantage is that it has a lot of context. It can look very far forward and backward. But a downside is that it's inherently sequential, which means if you have a very long string of text, it slows down. It's very expensive to both do training and inference on an LSTM. LSTMs were the state of the art for doing NLP until transformers came along. The speaker this morning gave the paper "Attention is All You Need" that really started LLMs. But LSTMs are still good because, for certain types of use cases because they are smaller models that you can train and stuff. You can do training efficiently. So Sahan Farhudi was an intern of mine. He implemented this in 2020. It's now available in ICU4X already. It's available in ICU via a build option. It's also used in Firefox. Firefox looked at this and was like, we're actually pretty happy with this model. So if you go into Firefox and you give a Thai text, you're actually using this model right now. This is the only ML model that I'm aware of that's used in production for line segmentation. CNN. Okay, so this is a convolutional neural network. You've probably heard this word a lot because people are talking all about neural networks and machine learning and everything. Cool, so CNN. So this architecture, it uses a neural network where you have different layers. The layers feed into the next layer. I'm not going to give you a class on how neural networks work. You can find a bajillion videos on YouTube to explain to you how neural networks work. The main thing here is that relative to the LSTM, we're able to do this all in parallel. Rather than the LSTM, which is sequential, where you have to read one character at a time, you can do this in parallel. You can take the entire string of text, run it through a matrix, and then you get the output at the end. Sheng Hong, who's the same one who did AdaBoost, also implemented the convolutional neural network. Two different models in one summer. Like when we accepted as a proposal for Google Summer of Code, we were just thinking he'd do this, and then he also gave us AdaBoost for free, which was pretty cool. And this also has experimental code in ICU4X. I'm also going to show you BudoX, because BudoX does ship a Thai model. So this is where I'm sort of showing like crossing between those two classes of problems. We can see how BudoX performs. Cool, so let's go ahead and compare model size. Okay, so for a particular language, we look at Thai a lot, but again, this applies not only to Thai, but it also applies to other languages in this region, Khmer and Burmese and Lao and many others, including minority languages, minority scripts. There's so many. So per language, the ICU dictionary, depending on which version you use, is between 100 and 200 kilobytes. The LSTM model is 36 kilobytes, so quite a bit smaller. CNN is 28 kilobytes, the BudoX is 33, so we're in that like 30 kilobyte range for the ML model versus a much, much bigger one for the dictionary. And again, this is per language. All of these are per language right now. A stretch goal of mine is to build a pan-language ML model. We're not there yet. If anyone wants to help do that, please talk to me afterwards. Let's look at performance. Okay, so this is where the numbers get a little scary. So let's look at F1 score first. F1 score is accuracy. It's, again, higher is better. So the F1 score for the ICU dictionary is in the 80s. It's actually better for the LSTM and the neural network. they actually exceed the performance of the dictionary. We saw that a little bit in CJK. It's actually better here. And one reason why I think it's better is because, again, these models are able to learn the structure of language so that if it sees a word it's never seen before that's not in the dictionary, it can still get the correct answer. So that's one reason I think about why we see these numbers be better here. Latency. I have to show this because I wish these numbers were a little bit better. But yeah, the ML models are slower. Again, we're competing against like a textbook algorithm, and we're doing like matrix multiplications. So like, it's slower. We've gotten that number down to about 300x in Rust. These numbers you're seeing here are based on the NumPy implementation, which is in Python. So the numbers are going to be a little bit different when we get into Rust. We have gotten this down to 300x in Rust, which again is slower. But you know, again, Firefox deploys this. They've looked at the data, and they're like, size is smaller, accuracy is higher. The amount of text that we need to do at a certain time, this is just a blip in the performance of layout on a web page. All fine with us, right? If you're just segmenting, you know, maybe 100 code points at a time, like the difference between, you know, 1 microsecond and 300 microseconds is maybe not a big enough difference for you when you're looking at that scale. So another thing here is that AdaBoost is kind of competitive. It is lower, the UTW. It's quite fast. It's quite fast, and it's not quite as accurate. This is not something we spent a lot of time on. We added this to the slides just like 2 days ago, so I haven't really looked too much at that row. I think it's promising enough that it's probably something to investigate further, see if we can get, if we do some more optimizations with the model, see if we can get the AdaBoost accuracy up to be more competitive, because the performance is just so high that it makes it really compelling. Yeah, this is my slide here. My disclaimer: the ML models remain slower, dictionary models remain faster, but again, so much smaller and more accurate in a lot of cases. That's why we offer you either a solution. I'm not going to say there's a one-size-fits-all solution. Dictionary is still here. It's going to stay here for as long as it's still, you know, so fast, which is probably going to be a long time. So when you're looking at these models, like, these are some of the things that you should be evaluating. I'm not saying you should definitely do this thing or definitely do that thing. Just weigh the trade-offs based on what you need. Cool. Okay, text samples. This is my text sample for Southeast Asian. I ran this string. This is a string from the text from Fitzgerald and from the Google Test Corpora repository project. Which, if you're interested, if you need like, one problem with training these models is where do you get the data. That's been a really big challenge for us. So what I've done is I've worked on actually getting Project Gutenberg texts and creating breakpoints in those texts that we can train on. So it's a little bit of using the output of a big model to train a smaller model. If you're interested in this, if you're in a place where you need more text, more corpora to train on, talk to me, because I've thought about this problem a lot. So the dictionary does what it does. One thing I want to point out here with Mr. Mumbles is the last name. It's a surname. The dictionary doesn't know that word because it's a surname. It's a phonetic word. This is one of the most common errors that we see in all the models, but especially in dictionaries, that if there's a phonetic word where like these Thai characters literally make the sounds mumbles, right? And that's not a word that looks like any other Thai word. It is a phonetic transliteration of the word. So that's one place where the models break down a little bit. I do want to point out that the ML models at least learned mom, because that's a common word used for mother. And the ML models learned that even though it's not in the dictionary. So that's kind of cool. Another thing here is, yeah, the 3 is done slightly differently between the different models. It's one word, and the CNN is the only one that figured out that it's actually one word and not 2 words. Yeah, UTW it had no idea what to do with Mr. Mumbles. It just was like, I'm giving up here. I'm just going to skip that whole section of the text. It didn't find any breakpoints there. Cool. Next steps. Cool. This is my last slide, which means we have a little bit of time for questions. I know this was a lot of content. I'm really excited to present about this because I think it's a really high impact problem. It's a problem that a lot of people haven't really spent as much time looking at as they really should. And I'm really glad that there's, I started here, there were like 20 people in the audience. Now there's like 40 people. Like a lot of people came in while I was giving the talk, so I appreciate that because this means a lot to me, and there's really so much more work that needs to be done in this space. There's a lot of opportunity to improve the accuracy and the experience for users who are using any type of application, like in any kind of language, both majority languages and minority languages, both. Like there's so much opportunity here to move the needle. It's, in my opinion, it's one of the most like underinvested but also critical problems in this industry, in the internationalization industry. So here's different ways that you can contribute. Use the ML models, provide feedback, help make them better. Help us with data collection. I mentioned that a little bit earlier, how we're sort of using the output of a big model to train a small model. Like data collection is really important. Exploring hybrid models. This is an idea that Shenghong had, where you can, can we improve the performance or the accuracy by sort of taking the best parts of an ML model and the best parts of a dictionary model and put them together? That's a really cool question. Another thing is training on multilingual data. Again, I would really like to get to the point where we can say that we have just a single neural network model maybe for like all Southeast Asian scripts. I think that's totally a doable problem. It's just someone needs to do it. Implementation engineering work. We got these in ICU4X because that's sort of been our test bed for where we can implement these things in Rust. We need to polish that code up a little bit, work on performance and so forth. Maybe also get implementations in other languages, possibly. And project management. I'm personally the person who's been pushing for this, and I would like to be not the only person who's really invested in this problem. So anyone here who's also interested in this problem, project management, help mentoring people and onboarding people is also really important. These QR codes, social media. I think these are all my social medias, so you can pick which one you like best. Cool. Thank you to our sponsors. And I was supposed to show this slide. We have about 7 minutes for questions. So are we doing passing a mic, or are we doing lining up to the mic? Alongo says line up to the mic. So if you want to ask a question, get up, walk to the mic, and ask your question, please. Thank you. First question here. You don't have to wait. You can get in line so that we don't have to wait for you to do that. Cool. What's your name and organization and your question?
Adil Alawi, Apple, and I can't hear if the mic is working. Is that working?
It's working great.
Excellent. So you say that, of course, the ML model inference is longer than the algorithm, but have you done these timings by using because we're now getting ML inference on chips on devices. So do you actually push these through the ML model inference on the silicon that is supposedly optimized for that, and does that help?
So all the numbers you've seen are based on the extent of how we can push a CPU chip. So we're using SIMD, for example, and we're really pushing the CPU chips as much as we can. I think most of the numbers you saw are probably on x86. We've also done them on ARM chips to sort of get those numbers. We haven't spent the time to get those numbers on ML chips, on GPUs and TPUs and such, especially ones that are on device. That might improve it a lot. We just haven't done that. It's one of the things on the to-do list, right? So that's a great question. I'm glad you asked.
Right. And one more thing is, okay, this is ML segmentation. What other areas of Unicode would benefit from ML?
Oh, that's an interesting question. I think that one thing I've really wanted to see for a long time is can we use LLMs to generate better CLDR data, improve the quality of CLDR data? I have more ideas. We can talk later about that. But yeah, those are sort of some of the big things. Confusables is another thing. Can we use it for confusables, which is you have, you have for example, if you're going to a website, it looks like it says google.com, but actually it's spelled in Cyrillic characters. Can we use ML for doing confusables? We actually had a Google Summer of Code contributor contribute an ML model for that, and it's currently in the bucket of things that someone needs to actually process and maybe generate actual confusables data for it. So those are a couple examples. Thank you. Another question?
Yes. So when it comes to keeping these models like up to date, and when it comes to the dictionary approach, one of the things you have to do is keep up to date with the language, because new words are coming into existence, or becoming popular or less popular as time goes on, and also people's names that you may have in the dictionary may change. How do you keep that stuff up to date? Is there a process in place yet to handle such situations?
So your question is, since languages change and names get added to the language, how do we learn, how do we keep the models updated for this? Yeah, so I mentioned a little bit earlier how the ML models can learn about the semantic structure of language. So it can learn like this is probably a word because it ends with an ing, right? Of course, in the Thai equivalent of that, or the Chinese equivalent of that. As far as learning phonetic words, it's a problem of so sometimes it works, sometimes it doesn't work. I don't really have a very specific answer for you. I know that, for example, one bug that we were looking at is like the word SIM, which is like a SIM card in like your phone. That's not a word in the dictionary, but the ML model actually learned that word somehow, and was able to, and actually gave the correct segment for that word without us having to change anything. So I think there are definitely some examples there.
Let me rephrase it slightly differently. How do you fix bugs?
So that's one example of this this hybrid ML dictionary approach. Could be where you can have a dictionary for like overrides, and that could be one way to fix those bugs. Another way to fix the bugs is just like improve your training data set until it works. But I think that because there are cases, like you said, where like I just want to fix this one bug because like this customer I have like just really wants this one particular word segmented in this way. That's where I think a hybrid model is probably the best bet. We don't have that yet, but it's something where I would like to see. Great questions. I love both those questions. I've got time for maybe one or two quick questions or one more question. Please ask. The microphones are right there. I'm not scary. Here we go.
Yeah, thank you for the presentation. I was just curious, when it comes to improving the quality and checking the output, are you working with linguists for each language in the sense that it's like crowdsourced linguist work or anything like that? I was just curious.
Great question. Yeah. So for the data sets that I presented in this talk for the Cantonese and Chinese and Thai, we have public data sets that we're using.
Okay.
So those data sets have already gone through this process of like getting vetted by linguists and such. However, for some of the longer tail languages, we don't have those resources. That's the point number 2, data collection. We're using like, for those languages where we sort of have to get what we can get, which is like take the output of a large model and use it to train a small model, which is not ideal because that doesn't have there's no human in the loop there. I would like to be in the situation where like I can say authoritatively like this is the correct answer for those longer tail languages. So if that's something that you're interested in, please talk to me.
Thank you.
And I don't see any other questions. We're just about at time. So yeah, just one more chance to scan the QR codes. Come find me. I'll be here for the rest of today. I'll be here also tomorrow. Please come talk, contribute. There's my email also up there in the corner. That's another great way to get in contact with me. And thank you all for coming and sharing this really important topic with me and learning about it and hopefully also contributing back and evangelizing it. So thank you all.